Have you ever wondered what's holding everything together? I mean, really holding it together? The salt in your shaker, the water in your glass, even you. Well, it's all thanks to an invisible force, a sort of atomic social club. So what's the secret password to get in? Let's find out.
So what is this powerful force? Well, the short answer is chemical bonds. It's how atoms connect with each other to build, well, everything. And you know what? The reason they do this, the motivation behind every single one of these connections, all comes down to a simple universal quest for stability.
You see, in the world of atoms, it's kind of like a giant high school. Not everyone is created equal. Some atoms are just naturally stable and perfectly content on their own, while most others are desperately trying to find that same kind of balance. And that search, that's what drives all of chemistry.
So let's meet the atomic VIPs, the noble gases. Think of them as the cool, unbothered A-list celebrities of the periodic table. They have a full outer shell of electrons, which is basically atomic nirvana. They're stable, they're non-reactive, and they rarely feel the need to bond with anyone else. They are the absolute role models for every other atom out there.
This whole obsession with getting that perfect full outer shell, it's so common it actually has a name, the octet rule. It's this simple idea that most atoms just really want to have 8 electrons in their outermost shell, just like their noble gas heroes. And to do that, they've got to interact. They have to gain, lose, or share electrons. This is the entire motivation behind chemical bonds.
Okay, so that's the goal. Get stable. But if most atoms aren't noble gases, how do they actually pull it off? What's their game plan for reaching that stable state? Well, it turns out they have 2 main strategies they can use.
And that leads us to these 2 very different approaches. On one side, you've got ionic bonding, that's the give and take strategy, and on the other, you have covalent bonding, which is all about sharing is caring. These 2 methods are responsible for pretty much everything around us. So let's break them down, starting with the givers and the takers.
First up, ionic bonds. This one is, well, it's a bit of a drama. It's a relationship that forms between a metal and a non-metal atom. And it's a story of complete transfer. One atom straight up gives an electron away, and another one just as eagerly snatches it up.
The classic example here is just plain old table salt, sodium chloride. So you've got sodium, a metal, with one lonely electron in its outer shell that it's just desperate to get rid of. Then you've got chlorine, a nonmetal, who is this close to being stable. It just needs one more electron. You can see where this is going, right? Sodium just hands its electron over to chlorine. Bam! Now sodium has a positive charge, chlorine has a negative charge. And just like little magnets, these opposites attract, locking them together in a super strong bond.
And that's the real key to understanding an ionic bond. The bond isn't really the electron hopping over. Nope, the bond is the powerful electrostatic force, that intense magnetic pull between the newly positive ion and the newly negative ion. That's what holds the whole thing together.
But you know what happens when atoms aren't willing to just give their electrons away? That brings us to strategy number 2, covalent bonding. This is the language of teamwork, of cooperation, of sharing.
So why share instead of just giving and taking? Well, covalent bonds usually form between 2 nonmetal atoms, and nonmetals are all pretty stingy. They have a strong grip on their own electrons. Since neither one really wants to lose an electron, they come up with a brilliant compromise. They'll just share them instead.
Let's look at maybe the most famous molecule ever, water, H2O. An oxygen atom needs 2 more electrons to be stable. Each of the 2 hydrogen atoms needs just 1. So they team up. The oxygen atom shares 1 electron with each hydrogen, and in turn, each hydrogen shares its single electron back with the oxygen. And the result? Everybody's happy. Oxygen feels like it has a stable octet, and both hydrogens feel like they have full outer shells. That is the power of sharing.
Okay, need a quick way to remember all this? Here's a simple cheat code. If you see a metal and a non-metal hooking up, it's going to be an ionic bond. If you see 2 non-metals, they're sharing, and it's a covalent bond. It's a really handy rule of thumb to figure out what you're looking at.
All right, so we've got these 2 totally different ways of bonding. One's based on charged attraction, the other's based on sharing. But can you actually see this difference play out in the real world? Oh, absolutely. Let's put them to the test.
So here's the challenge. It's pretty simple. We're going to take our ionic compound, salt, and our covalent compound, sugar. We'll dissolve both in water and then see what happens when we try to pass an electric current through the solutions.
First, the salt. In its solid crystal form, All those positive and negative ions are locked up tight in a grid. They can't move, so electricity can't flow. But the second you dissolve that salt in water, poof! The ions break free and are now swimming around, and those mobile charges are the perfect couriers for an electrical current. So yep, salt water conducts electricity.
Now, let's try this sugar. Sugar's a covalent molecule, remember? So when it dissolves, it doesn't break apart into charged ions. Instead, the whole neutral sugar molecules just drift away from each other in the water. Since there are no free-floating charges, there's absolutely nothing to carry a current. The result? Sugar water does not conduct electricity. Not at all.
And there you have it, the results of our test, clear as day. This simple experiment with electricity totally reveals the true nature of each bond. The ability to conduct electricity when it's dissolved in water is a dead giveaway for an ionic compound, because it proves there are free-moving ions in there. It's a real, observable difference that's rooted directly in how they're built.
Now, this isn't just some neat chemistry trick. This whole atomic drama, this constant quest for stability through giving, taking, and sharing electrons, is literally what builds the world around us.
I mean, just stop and think about how common these bonds are in your everyday life. Ionic bonds give us the salt on our tables, the calcium carbonate that makes up eggshells and chalk. Meanwhile, covalent bonds form the water we drink, the butane fuel in a lighter, and of course the sugar in our food. These two simple strategies are truly the building blocks of our reality. So really think about that. Everything tangible, everything you can touch and see, is a product of atoms following these basic rules. A ridiculously vast and complex world, all built on just two fundamental strategies for finding stability. It's an incredible thought.
And that leaves us with a final question to chew on. We figured out these fundamental bonds that have built our entire planet. But what comes next? As we learn more about how to manipulate and even create new types of bonds, what incredible new materials and technologies are we going to build in the future? Thanks for watching.